Okay, so this P7 video is for the Hertzsprung-Russell Diagram and stellar evolution. First of all, we need to know what the Hertzsprung-Russell Diagram is. So it's basically a way of grouping stars together. And what we do is we have luminosity on the vertical axis, and we have temperature on the horizontal axis. And slightly weirdly, the higher temperatures, so hotter stars, are on the left-hand side of the diagram, and the cooler stars are on the right. So that's the reverse direction that you would normally expect to have a plot on that diagram. And what we find is we have a main sequence of stars. So most stars sit on this thing called the main sequence. And the main sequence is where hydrogen fusion is happening, which most stars do for the majority of their life. We have the very larger, blue, hotter stars to the left-hand side of the diagram. And because they're larger and hotter, they have a higher luminosity. The two things that affect the luminosity of the star are its size and the temperature. And as we go down and to the right, the temperature is lower, and we have smaller stars, which are therefore giving out much less light. They have a lower luminosity. So, the other key difference is that the stars on the top left of the diagram have a very high rate of fusion, so their lifetime is extremely short, 10 million years. It's not obviously extremely short in human terms, but in terms of the universe, right, which is approximately 13.7 billion years old, 10 million years is a very short amount of time. And then at the opposite end of the spectrum, the stars at the bottom right, because they're very small, they can't sustain a high temperature and pressure in their core. They have a very low fusion rate and can last for, approximately 1 trillion years, so much longer than the age of the universe so far. And then we have stars somewhere in the middle, like our Sun, and our Sun should last around about 10 billion years. So it's about halfway through its lifetime at the moment. And then the other groups of stars we have are the red giants, so they're off to the little bit up and to the right on the diagram, so they are more luminous and slightly cooler than the sort of our Sun would be, and larger. That's why they're called giants. And then we have supergiants, which are even larger and therefore even more luminous above the red giants. And the bottom left corner we have the white dwarfs. So you need to be able to label those sections of the Hertzsprung-Russell diagram: the main sequence, the red giants, the supergiants, and the white dwarfs. And we also need to be able to talk about how two different types of star evolve. You need to be able to do that as a sequence of descriptive writing, but it's useful to look at where they move on the Hertzsprung-Russell diagram, because it will help to remember what's going on in the sequence. So the first one we're going to look at is a star like our Sun. We have to remember that stars form from collapsing clouds of gas, mainly hydrogen and some helium. And what happens is, as the cloud collapses, it collapses because its own gravity is pulling it together, so it's self-gravity pulling it together. And that means at the start it's got a lot of gravitational potential energy that is converted into kinetic energy as the collapse happens, and then all the collisions between the various atoms in the cloud basically turn that kinetic energy into thermal energy, and we get what's called a protostar as fusion starts to happen in the core. Now you'll notice what happened was the cloud initially was quite large and therefore had a reasonably high luminosity, even though it was quite cool. As it collapsed, the temperature increased, but the luminosity dropped, and that's only because we've got less sort of surface area emitting light. As the cloud collapses, its surface area shrinks. Even though it's hotter, its luminosity drops slightly. Okay, so once we get to the main sequence, then we've got hydrogen fusion into helium going on in the core, and the star stabilizes in this state on the main sequence for billions of years, like we've already seen. Okay, and what's happening here basically is that gravity is still trying to pull the star together and compress it, and the radiation pressure produced by the fusion process is pushing back out against that, and the star stays stable whilst the hydrogen fusion is going on. But eventually the helium starts to build up in the core, and the conditions for hydrogen fusion don't exist anymore where the hydrogen is, which is now a little bit further away from the core because the helium's there. And when that happens, there's nothing to stop the collapse continuing of the star, and the core collapses first, and what we get is a core collapse, and that core collapse again releases a lot of gravitational potential energy into thermal energy, which heats the outer layers of the star, causing them to expand. The photosphere, that is the outer layer of the star where the light is emitted from. Those outer layers expand and they will eventually cool, and that's why we get the red giant. Okay, Again, the luminosity is increased from the main sequence because the star is larger. The temperature has decreased slightly because the photosphere cools when it expands. So, that's the red giant, and what's actually going on there is that now instead of fusing hydrogen into helium, we are now fusing helium in the core to elements like carbon, nitrogen and oxygen. Okay, that's something called the Cno cycle that happens in these red giants. Now, a star like our Sun doesn't have enough mass to fuse beyond those elements. Okay, basically, to get further along the periodic table in fusion, you need a star of larger mass because you need higher and higher temperature and pressure to get the next fusion reaction to happen along the sequence. So what happens at the end of that fusion is that the core collapses even further, and it heats the outer layers so much that they swell up even more, and they are basically blown off the star in this shockwave and form what's called a planetary nebula. So I'll just show you that one more time. There's the red giant star. Okay, core collapses, the outer layers expand even more, and they're just blown off the star. Okay, now what's happening to the luminosity during that point is due to the heating of the, thanks to the core collapse, the luminosity increases initially as the star's getting larger and slightly hotter. And then when the outer layers are blown off, they're not really part of the star anymore, and all that's left is this very compacted core, which forms basically the white dwarf. Now it's very, very hot, which is why we're over on the left-hand side of the diagram, but its luminosity is quite low because it's so small. There's not a lot of area to give out the light. Now, during the white dwarf stage, this is the important thing, no more fusion occurs. It's fused as far as it can't create the conditions for any more fusion, so it's not releasing energy that's locked up in the nucleus of in the nuclei of the atoms in that star anymore. So as a result of that, all it does now is lose the energy it's got, and it gradually cools down. So that white dwarf will cool down, it will get less luminous because its temperature is dropping, it will go to the right on the diagram because its temperature is dropping, and it sort of cools and fades away, and eventually it's very difficult to detect it at all because it's hardly giving out any visible light. So that's the sequence of events for a star that is similar to our Sun. Okay, you need to be able to reproduce whole or parts of that. A 6 marker might not ask you about the entire process, but it might ask you to explain what happens to a star like our Sun from the main sequence, in which case you'd go from step 3 and you wouldn't worry about step 1 and 2. It might ask you to describe the formation of the star and what happens to it up to the red giant stage. So you need to be able to pick sections out in order to focus on the marks that you're going to need to get for the 6 markers. Okay. So that's a star like our Sun. The other one you need to know is a star that is significantly heavier than our Sun. So we'll look at that on the diagram as well. Again, we start with a cloud of gas, mainly hydrogen and helium again. And this cloud is obviously much larger because it's going to produce a larger star. Again, it's very luminous, even though it's relatively cool, just because it's so big. As it collapses, the luminosity drops, but the temperature increases again, due to this same process of gravitational potential energy being converted to kinetic and then to thermal. We get the protostar and the fusion starts to happen, and then it stabilizes on the main sequence again for a much shorter period of time. Because the star is more massive, the fusion rate is much higher. Okay, but again, once it can't fuse hydrogen anymore into helium, it does the same sort of process as our Sun would do, except instead of swelling to a giant star, it swells into a supergiant. Okay, but the same basic idea is up to this point. The star is now fusing helium into carbon, nitrogen and oxygen, but what it can do, which our Sun couldn't do, or a star similar to our Sun, is that this star has enough mass to create the conditions, the higher temperature and pressure needed to fuse past carbon, nitrogen and oxygen. And in fact, it can fuse all the way up to element number 26, which is iron. And iron, it happens, has the most stable nucleus of any element. So once it gets to that point, it's impossible for it to release energy by fusion anymore, because it's at the most stable point. So even though it can create these higher fusion reactions, we again end up with a situation where the star is not able to maintain fusion, and because of that it will collapse because there's no radiation pressure anymore. The collapse here, because the star is much larger, is much more catastrophic. The star essentially completely collapses on itself in a very, very short amount of time, and we get a supernova. So that star has now vanished. The reason I've not shown the supernova is because the supernova is so bright that it's way off the top left of the diagram. Okay, it is incredibly hot, 1 trillion degrees Kelvin, and it is incredibly bright. a supernova in a galaxy can typically outshine all the other stars in that galaxy during its initial phases, so hundreds of billions of main sequence star brightness. Okay? And what that does is, if you think about it, in the early universe, we had hydrogen and helium, but all the other elements have come from somewhere. We've got explanations so far for where everything up to iron has come from, but the gravitational energy released in that massive collapse of the core of this huge star is enough to actually put energy in to fuse elements past iron in the periodic table. So all the elements past iron, past element number 26, were created in supernova explosions. Okay? And then what happens then is that the gravity is so strong here that we get what's called a neutron star. And basically, if you think about a normal atom, it has protons, neutrons, and electrons. And a normal atom has an equal number of protons and electrons. The gravity is so strong in this situation that it forces the electrons into the protons and turns them into neutrons. Okay, so it's kind of like a reverse beta decay. Okay. What that basically turns the star into is a giant atomic nucleus, 12 kilometers across, roughly, neutron stars, but it's all nucleus. There's none of the gaps that you have in a normal atom between the nuclei. That means it's incredibly dense, billions of times the density of normal matter. But again, we're in the same situation. It can't release any more energy by fusion. It's incredibly hot to start with. Because it's so small, actually, we can't plot the neutron star on the Hertzsprung-Russell diagram, because despite its massive initial temperature, it's so small that its luminosity is very low. So it would actually be off the bottom left of the diagram. And it does a similar thing to the white dwarfs. It will cool gradually, okay? And eventually, once it's completely cooled, it won't be visible anymore. The other thing you need to know is the alternative final stage. If you have a star with an even higher initial mass than one that will form a neutron star, then gravity is so strong that it even compresses all the neutrons together and you get a black hole. And nobody really understands what exactly a black hole is in terms of what's inside it. But the reason it's the black hole is that the gravity then is so strong at what we call the event horizon on the surface of the black hole that not even light can escape it. So that's why it's black. So there are the two types of stellar evolution that you need to know. Certainly worth remembering how the first one fits on the Hertzsprung-Russell diagram. As you can see, that only the first few stages of the very massive stars fit on the Hertzsprung-Russell diagram. But still useful to possibly be able to refer to those things. And if you're asked to describe the evolution of a star, one thing you could do is sketch the Hertzsprung-Russell diagram and the route that the star takes, depending on which one you're asked for. Because that would be a useful thing to hang your discussion off, and hopefully might help you remember the stages a bit better. Okay.